Hello friends, today's question: a uniform disk of mass m and radius r is projected horizontally with a velocity v0 on a rough horizontal floor so that it starts off with a purely sliding motion at t is equal to 0. After t0 second, it acquires a purely rolling motion as shown in figure. Calculate the velocity of center of mass of the disk at t is equal to 0, at t0. B. Assuming the coefficient of friction to be mu, calculate T0. Also calculate the work done by the frictional force as a function of time and the total work done by it over a time t much longer than T0. So we have the disk whose mass is given as m, and initially at time t is equal to 0, it is in the motion of pure sliding, and at t is equal to T0, the sliding motion is changing into a pure rolling motion. So let us redraw the figure and divide into two parts. First is when it is a pure sliding, and second one when it will be pure rolling. So this is pure sliding and this is pure rolling, and in case of sliding it is given an initial velocity, horizontal velocity of v0. So this is velocity of v0, and suppose this is the surface on which it is sliding or rolling. So there will be a frictional force which will be acting in the opposite direction. Let us suppose that is Fr, and in the downward direction we are going to have mg, and there will be a normal which will be acting in upward direction, and there is no angular velocity, so that will be equal to 0 in case of pure sliding. Now in case of pure rolling, we assume that the velocity of the center of mass is now given as v, and it is rolling with the angular velocity of omega. Okay. And so we have two type motions, pure sliding and pure rolling. So in case of pure sliding, you can say a frictional force Fr will act leftward in the direction, whereas in case of pure rolling motion, the friction is 0 as there is no relative motion between at the point of contact. So you can say friction is 0 as there is no relative motion at point of contact. So let us suppose this is our point of contact, and let us suppose we are calling it as P, point of contact P. Secondly, the torque will be produced by the frictional force. Torque will be produced due to friction force. So therefore there will be torque produced, and its radius is given as r. So in the opposite direction, so this will be the force. Now in the pure rolling case, this Fr is the force which will be generating the torque with the angular velocity omega, or we can say with the acceleration also as alpha. Okay. So let us consider one by one. So first is our pure sliding. So which is basically translation motion, which we consider that it is sliding, there is no rolling. You can say translational motion, so means sliding, no rolling. So it is given in the question itself that the disk is projected with the velocity v0. The disk is projected with velocity which is given as v0, and a frictional force Fr acting on it. Frictional force Fr acts on the disk, and we know that the frictional force Fr is equal to coefficient of friction multiplied by normal, and normal will be in this case mg, so this will be mu mg. So because of this frictional force, the disk will be in a retarding motion. So you can say that the Fr causes a retardation. Let us suppose that is given as A. Causes retardation. Let us suppose that is given as A, and which will be equal to Fr divided by M. And we already know that Fr is equal to mu mg. So we get A is equal to mu mg divided by M. M and M cancels out. So we get the acceleration is equal to mu g. And we can find out the velocity at time t0. Velocity at time t0, let us suppose that is given as v, and v will be equal to initial velocity minus a time t0, and initial velocity u is given as v0. So therefore we can say that v will be equal to u0 minus a multiplied by t0. Substituting value of a, we get v0 minus mu g multiplied by t0. So this is a velocity after time t0. And the rolling motion starts at time t is equal to t0. So basically this equation represents the velocity of the center of mass at the time t is equal to t0. Next, let us consider the rotational motion now. Rotational motion, the friction is going to provide the torque. So we can say frictional force Fr provides the torque causing the angular acceleration alpha, causing angular acceleration alpha. Therefore, we can say that torque will be equal to frictional force multiply perpendicular distance r, which will be equal to I multiplied by alpha, where I is moment of inertia of disk, which will be equal to half m r square, and Fr we already know is our frictional force. So we substitute the value, we get mu mg multiplied by r is equal to half m r square, and we have multiplied by alpha. So this r cancel out this square. So from here we can say our alpha is equal to 2, mass also cancel out, we get this is 2 mu g divided by r. So this is the angular acceleration. Next, we can also find out our angular velocity. And in case of angular velocity, we know that the angular velocity omega is equal to alpha multiplied by t naught. So substituting value of alpha, we can find out our angular velocity. So we can say angular velocity omega will be equal to alpha multiplied by t naught excuse me, and substituting the value of alpha, we get 2 mu g upon r multiplied by t naught. So this is the angular velocity at time is equal to t naught, because initial angular velocity is equal to 0. So we can say omega is equal to omega naught and plus alpha t. In this case, your initial angular velocity, that is omega naught, is equal to 0. From here we can say initial angular velocity is 0. Initial angular velocity is equal to 0. So using the standard formula that omega is equal to omega naught plus alpha t naught, we get this expression. Now for pure rolling, we also know that the velocity of the center of mass and angular velocity relationship. So we can say for pure rolling, we have v is equal to omega r, and from equation 1, let us suppose this is equation 1, and from equation 1 we know that v is equal to v naught minus mu g t naught. Now substituting the value, we get v is our, in this equation we get v naught minus mu g t naught, and also substituting value of omega, omega is our 2 mu g upon r multiplied by t naught and whole term divided by r. So this r cancel out with r, and on the right side we are left with 2 mu g and t naught. So from here we can write that our v naught will be equal to 2 mu g t naught plus mu g t naught. So this gives us 3 mu g t naught, and from here we can find out t naught. T naught is equal to v naught divided by 3 mu g. So we found out the time t naught at which the pure rolling is going to start in terms of the velocity, initial velocity, that is v naught. Okay. Now once again we are going to use equation number 1 and find out what will be the velocity v. Okay, we already found out v naught in terms of t naught. We found out v naught in terms of t naught. Now we are going to find out v in terms of t naught using once again equation number 1. So we say using equation 1 or from equation 1 we have v is equal to v naught minus, and it is mu g multiplied by t naught, and t naught we found out v naught divided by mu g, and this is 3 mu g. Mu g and mu g cancels out, so we are left with v naught minus v naught by 3. So this gives us that v is equal to 2 by 3 v naught. So we found out that when the pure rolling motion starts, the velocity of the center of mass in terms of the initial velocity v naught. Next, we are going to do the part B now. Okay, work done by the friction. Okay, in the first part, we are supposed to calculate the velocity of center of mass of disk at time t is equal to t naught. So we found out this is the velocity of the center of mass at time t is equal to t naught. This is the velocity of center of mass at time, center of mass of disk at time t naught. Now we come to the part B, in which we have to find out the work done. Work done by the friction. Done by friction. So we are going to, so we can say work done by the friction up to time t equal to t naught. Okay. Now here friction, in sliding as well as rolling, friction is present in both the cases. The way it acts is different. In sliding, the friction is acting as a retarding motion, whereas in rolling, the friction is producing our angular acceleration. So way the friction is acting is different rather. So in the first case, we are going to find out the work done separately, and in the second case, that is pure rolling case, we are also going to find out the work done by the friction. Because when friction is absent, especially in the pure rolling case, we can say the energy is going to remain conserved. Where in the first part, pure sliding, friction is a conservative. So because of that, we cannot use the conservation energy. So in the second part, we are going to use the conservation. In the first part, we are going to find out the friction, work done by the friction by subtracting the initial as well as finite kinetic energy. Okay. So we can say that work done by friction up to time t is equal to t naught. This will be equal to kinetic energy initial minus kinetic energy final. And kinetic energy initial will be equal to half m v naught square, and kinetic energy final, as the motion is now both translational as well as rotational, so we can say kinetic energy final will be equal to half mv square plus half I omega square. So once again we are going to solve it, substitute the value, and we also know that our V, let me write it here, we know that V is equal to V naught minus mu gt. We also know that omega is equal to 2 mu gt upon r, and I is equal to half m r square. So therefore we can say our kinetic energy final will be equal to half m, substituting value of V, which is V naught minus mu gt whole square, and we have plus half moment of inertia we already know is 1 by 2 and mr square, and omega square is our 2 mu gt upon r, and this is whole square. This is now a little bit lengthy calculation, so this comes as half m, this will be V naught square plus mu square g square t square, and this will be minus 2 V naught mu g t, and this comes as plus, we are left with 1 by 4 mr square multiplied by this will be 4 mu square g square t square upon r square. 4 and 4 cancels out and r square goes with r square, and taking throughout 1 by 2 m as common, so we can write this as 1 by 2 m, and we are left with this as V naught square plus mu square g square t square minus 2 V naught mu g t, and this comes as plus, this will be about 2 mu square g square and t square. This is equal to half m, and we get this as V naught square plus this will be our 3 mu square g square t square minus 2 V naught mu g t. So it means now we found out kinetic energy final. Kinetic initial we already know, we are substituting in this formula. Okay. So we can say work done by friction, work done by friction will be equal to half m V naught square sorry yep, this I this good, and V naught, this will be our minus, and this comes as half m V naught square plus 3 mu square g square t square minus 2 V naught mu g t. So we just open the bracket and subtract it. These two terms are going to cancel with each other, and we get this as half m 1 by 2 m this will be equal to our minus, and this is 3 mu square g square t square and minus 2 V naught G, sorry, let me write it again. This is equal to minus 1 by 2m, and we have 3 mu square G square T square, and we get this minus 2, and we have here V naught mu G T. Okay, so this is the work done in the first part due to friction. Now find out for time t is greater than 0. For t greater than t naught, so we already know that disk rolls out without slipping. Disk rolls without slipping. Kinetic energy remain constant. And friction you can say it doesn't do any work. Okay? Or we can say from here, friction force Fr does no further work. The way the friction force work Fr is only providing the angular acceleration, or we can say your angular velocity. Okay. So therefore, from here we can also say that Fr acts only to maintain the rolling without slipping. Rolling without slipping. Therefore, the energy will be conserved for t equal to t naught. Therefore, energy will be conserved for t greater than t naught. So it means the work done by the friction will be a little bit longer than t is equal to t naught, which was said in the question also. Okay, the total work done by it over time t is much longer than t naught. You can say from here that thus the total work done by friction over time is much longer than t naught. So therefore, we can say that work done for the friction will be equal to your kinetic energy final minus kinetic energy initial. Okay, and this is for t greater than t naught, and this is also for t greater than t naught. So you're substituting the value. Final is the combination of both the translational as well as rotational value. The only difference will be now the time will be t naught, not t. So we get here half m t naught whole square plus half I omega t naught whole square minus half omega v naught square, sorry, m v naught square. And we already know that velocity at t naught is given as 2 v naught by 3, and angular velocity at t naught is also given as 2 mu t naught divided by 3. So substituting these values, we can write this as work done because of the friction is equal to half m, we have 2 v naught by 3 whole square, and plus moment of inertia we already know is half m r square, and this gets 2 mu naught t naught divided by 3, and minus we have half m v naught square. This is once again only the calculated part is left now. So taking half m, we get this as 4 v naught square upon 9 plus half, and this is half m r square multiplied by 4 one second, let me check whether omega formula is written correctly or not. Yeah, omega is equal to 2 mu g. Yeah, so this is wrong actually, my mistake. So this will be coming as equal to 2 by 3 v naught upon r, because v is our 2 v naught upon 3. Okay. So this is also, let me write it again. So we can write that the frictional force, work done by friction is equal to, we have half m 2 v naught divided by 3 whole square plus half moment of inertia, and it is equal to 2 v naught divided by 3r whole square, and minus half m v naught square. Yeah, that is correct. Now we solve it. So we get this as 1 by 2m. This is 4 v naught square upon 9 plus 1 by 2. This is 1 by 2 mr square, and this becomes 4 v naught square upon 9r square, and minus 1 by 2 m v naught square. So r square cancels with r square, and this goes by 2. So we are left with 1 by 2m 4 v naught square upon 9 plus 1 by 2m, we have 2 v naught square upon 9 minus 1 by 2m and v naught square. Taking 1 by 2m v naught square as common, so this becomes 1 by 2m v naught square. So we are left with this as 4 by 9 and plus 2 by 9, and this is our minus 1 by 2 m v naught square. So this becomes half m v naught square, 6 by 9 minus half m v naught square. Once again taking this common as throughout, so this is half m v naught square. We have 6 by 9 minus 1, and this comes as 1 by 2 m v naught square, and this is equal to minus 3 by 9. This goes by 3, so we get work done because of the friction is equal to minus 1 by 6 m v naught square. So this is our B part, which says that calculate the work done by the frictional force as a function of time and the total work done by it over a time t which is much longer than t naught. So we found out the work done as a function of time, frictional force rather, and the total work done. So this is the total work done, and the part first we found out the work done because of the frictional force. So this completes the question. Thank you.